Good afternoon. Welcome to SCA's webinar with Dr. Mohan Kelkar on upscaling for efficient flow simulation with Petrel. Before we start today's webinar, we'd like to ask a few questions about the demographics of our audience. So I'm going to share a couple of polling questions. And as I launch the first one, the question is, what is your primary discipline? Looks like we have a pretty good mix between petroleum engineers and geoscientists. Answers are coming in. It's about half and half. A few in the other category, but most of you have voted, so I'm going to go ahead and close and share the responses. We have 43% petroleum engineers, 52% geoscience, and 5% other. So my next question is, how many years of full-time experience do you have in the oil and gas industry? So we're getting our responses pretty quickly here. Looks like we have a good distribution. Quite a few in the 11 to 20 year range. Most of you have voted, so I'll go ahead and close and share the results. It looks like most, 43% are in the 11 to 20 year range, and we do have a pretty good spread across the entire range of experience. So thanks for that. So I'll go ahead and do the introductions. And before I introduce Mohan, I'd like to remind the audience that you're muted, but you can ask questions during the presentation using the Go to Webinar question feature, and we'll cover the Q&A at the end of the presentation. You will be anonymous. Let me see if I can progress. So the topic today is upscaling for efficient flow simulation with Petrel. And our speaker today is Dr. Mohan Kelkar. I've known Mohan for many years. He is Professor Emeritus and former chair of the Department of Petroleum Engineering at University of Tulsa, and he consults on projects around the world. And he's widely published, many technical presentations, co-author of 3 books. He's been a distinguished lecturer on the topic of integrated reservoir simulation. Mohan and I served on the International Board of Directors for SPE, and he's received a number of awards. So Mohan is speaking today to advertise the mentoring and consulting services he's providing through SCA. So if some of these questions are of interest to you, there's a contact phone number and an email address where you can contact us so we can put you in touch with Mohan Kelkar for consulting and mentoring services. We'd also like to remind you that we do offer a class on the principles of mapping with Petrel. The instructor of that class is Lori Green, and there's a description of what's covered in this class. This class is offered in-house, and so if you would like to have it set up in-house at your company, please let us know, and we'll let you know Lori's availability. Thanks for joining us for our free series of webinars. The next one that we have scheduled after today's is in July. July 15th, we have Dr. John Foster. He'll be speaking about energy data science and Python with introduction to pandas. And I'd like to remind you that SCA, in addition to training, we do provide consulting, direct hire services, and projects and studies. So without further ado, I'm going to give the presentation rights to you, Mohan, and let you take it away. So let me give you the sharing rights. Okay, so you should be able to share now.
Okay.
Great, and we do see your slides.
Thank you, Susan. How do you make the front screen smaller? Oh, okay, I can do it. Okay. I got it. All right, good afternoon. So this is a seminar, which is our the webinar, which I'm going to talk a little bit about upscaling. Why do we do it? And then I'm also going to demonstrate that using a couple of Petrel plugins. Um, so the first question we want to address is, why do we upscale? And for conventional reservoirs, basically, when you look at geocellular models, they contain multi-million cells. It's very difficult to actually flow model them without upscaling, and they tend to have long production history. And in general, they could have complex flow processes like compositional modeling, and that always takes more time. And if you can upscale them, reduce the number of grid blocks, then you can do the history matching as well as the flow simulation much faster. For unconventional reservoirs, the problems are even more complicated because you have large number of grid blocks and variable size grid cells, because if you want to model explicitly the fracture, the grid block cells can be a lot smaller than other parts of the reservoir. You have time step limitations because where you have the smallest grid blocks, you have the highest permeability. So that reduces the time step, and that increases the computational effort. You have high permeability contrasts from fracture to stimulated reservoir volume to matrix. And then a lot of times in unconventional reservoirs, you have complex physical mechanisms. You could have adsorption, you have permeability compaction as a function of pressure. Sometimes you have dual porosity models. And especially if you are trying to simulate huff and puff type of processes where you're injecting CO2 and producing oil, you need a compositional simulation, which can also result in significant additional time. So when you look at the history matching as a process, history matching is an inverse solution. Basically you have multiple solutions, and we need to account for the uncertainty in the future performance. And the way you do that is by matching multiple reservoir models and then predict the future performance. And a lot of times the data resolution can be different. So for example, in a lot of unconventional reservoirs, you want to match daily production, whereas in the field performance of conventional reservoirs, you may want to match monthly production. And there is a lot of conflict between local versus global history matches. Do you want to match the entire field performance, or you want to match individual well performance? Because of course the time required to simulate and match the local performance can be significantly greater than global history matches. And a lot of times when you're doing the history matching, if the field has a long history, then long forward modeling runtimes can result in significant under prediction of true future uncertainty, because ultimately you run out of time. It's taking so long to do the forward model that by the time you finish one history matching, you run out of time and you really haven't properly quantified the uncertainty. So one biggest advantage of upscaling is that if you can reduce the amount of time it takes to do history matching, you can then better quantify the uncertainties in the future performance. So what is an ideal upscaling? Ideal upscaling is the one which preserves the resolution of production data to a dynamic data. And you want to make sure that as much as possible, the dynamic characteristic of a fine scale model is preserved, because geologists and geophysicists have spent significant amount of time and effort in building that static model, and you want to capture as much heterogeneity from that model as possible, but at the same time making sure that we can capture the resolution of the production data. Hopefully, by doing this upscaling, we can reduce the forward modeling time, hopefully by at least an order of magnitude, perhaps several orders of magnitude. And that way, you can do multiple forward runs or history matches for proper quantification of uncertainty. So that's really the purpose of upscaling. And if you look at conventional reservoirs, you can see that we typically build the static model, and you want to go from static model to dynamic model, which obviously is coarser, and we need the appropriate way you can upscale. I don't know why the slides are moving forward without me doing it, but you have to upscale those models so that we can create the dynamic model and make sure that we have captured the uncertainty in the future performance. So what are the upscaling challenges typically? When you look at the fine scale model, say 5-layer model, and you want to upscale it to 2 layers, 3 layers, 4 layers, we have to think about what is the optimum of scaling. That means, should we go from 5 to 3 layers or 5 to 2 layers? And the second question is, what is the best combination of layers in which these layers should be combined so that we have properly captured the heterogeneity in the model? The second upscaling challenge we have is that on the fine scale, if there is no communication because sand is connected to shale and shale is connected to sand, and then if you want to upscale it, then it's quite possible that the property on the core scale on an average basis will create a communication. So basically, when there was no transmissibility or connectivity on a fine scale, you can artificially create a connectivity on a core scale. So if you really want to make sure that the fine scale connectivity is preserved on a core scale, then we want to make sure that it is preserved after upscaling. So I'm going to introduce you to two different plugins. One is called Connect Upgrade. This is developed by us, and that allows you to decide how many optimum number of layers you should use in a core scale model. So if you look at a very simple problem with 3 layers, 1 millidarcy, 10 millidarcy, and 25 millidarcy, which 2 layers you will combine? And people who have done simulation studies will immediately say you have to combine 10 and 25. But if you just look at the differences in the properties, then 1 and 10 has a smaller difference than 10 and 25. But the correct solution is indeed kind of combining 10 and 25. And the upgrade method we have proposed actually does that. And as a matter of fact, if you do simulation and look at the cumulative oil production, you'll find that combining 10 and 25 millidarcy layer is the right approach, and which will result in the correct match with the performance of a 3-layer model. The way upgrade works is that we actually look at a process by which we can look at the difference between, by combining the layers using proportional layering versus combining the layers using our method, how much is the difference between those two methods. And larger the difference, we believe that our method is working better. So this is one way we can look at it. And you can see the loss of heterogeneity as our calculation at the bottom, which looks at the difference between both the velocity and slowness. And if you are interested, we have written some papers, and we can obviously send you those papers. A lot of the work actually which we have incorporated in this upgrade is really developed by ourselves as well as Mike King from Texas A&M, and we really are using some of his methodologies in capturing some of these heterogeneity indexes. The other way you can look at the upgrading, this is one way you can look at, basically, is to look at this optimal design, and you can see that bigger the difference in, let me just change my pointer option, bigger the difference between the proportional layering and our method, we believe that bigger is the advantage for you in combining the layering. So this is one way you can decide how many layers you should choose using our methodology. Another way, which is much more traditional, is the loss of heterogeneity. So you can see that as you regressively reduce the number of layers, you can see that you lose some heterogeneity. So you could say that I can tolerate loss of 20% heterogeneity, 50% heterogeneity, and based on that information, you can choose certain number of layers, starting with the maximum number of layers. So you can use either of those two methods to decide how the layers should be picked. And what is new, we have just upgraded this upgrade model. What is new is that we can account for the grid block properties to determine the influence of those grid blocks. So obviously, if the reservoir quality is really bad in particular part of the reservoir, we weigh those grid blocks to a lower level, so we can combine those layers much higher than the layers where real action is and where you have most of the flow. We can provide the optimum number of layers based on the loss of heterogeneity, if that's the criteria you choose in deciding how many layers should be selected. And once you make a decision as to what is the right number of grid blocks you have selected, we automatically create the grid on a coarser level. I'm going to show you that methodology in just a second. We also have another plugin called Transmod, which accounts for the loss of connectivity when you have multiple layers. So if you have two layers and you just overlay on top of each other, if the lack of communication is not perfectly captured, perfectly aligned, then upscaling will create continuity which doesn't exist. And you want to make sure that the connectivity which you observe on a fine scale is still captured. So what we do is in the transmod is we upscale the properties using our own method. And again, this is a lot of this work was developed by Mike King. And we use the upscaling process so that we provide our own upscale properties and we make sure that the productivity, no matter where you drill the well, is still preserved, whether it's a horizontal well, whether it's a vertical well. And then we provide you the transmissibility calculations in both the z directions and transmissibility multipliers in x and y directions, so that once you use them, we have already captured the transmissibility or lack of connectivity which is observed in a fine scale. So let me show you an example. This is one of the most difficult reservoirs to model, SP10. It's a channelized system, and it has about 1.12 million cells, one injector, and 4 producers. And you can see that the original model is 85 layers. And I'm going to show you the results from both 27 layer, which we have created using the upgrade method, and the 9-layer model, which we have created also in upgrade method. So 27 layer, you could think about as an optimum number of layers, which you could utilize. And in general, the properties are reasonably preserved when you go from fine scale to coarse scale. But ultimately, the proof is in the pudding when we actually do the simulation. So here is the simulation results for both oil rates and water breakthrough. And you can very clearly see that when you look at the way the oil rate is decreasing and the water cut is increasing, that when we use both the combination of upgrade and transmod, our match with the water cut is really good and the breakthrough time is well preserved. And if I can just show you the next picture, which is for the earlier times, you can again very clearly see that the fine scale model matches really well with both the coarse scale models which we have developed, which is a 9-layer model and 27-layer model. Now, if we just use upgrade, we don't match the oil rate as well. It is still better than conventional proportional upscaling, but still is not as good. But once you combine both the upgrade and transmod, you can see the match is really good. So by using the combination of upgrade and transmod, you can say that you can reduce the total number of layers by an order of magnitude, definitely by 60 to 70%, and still reasonably preserve what we are seeing on a fine scale. Here's another example of a 550-layer model. This is a sandstone field, and you can see fine scale model, which is 575 layers, and then we build a coarse scale model, which is 80 layers. And again, you can look at the difference between proportional 80 layers, and you can see the results are quite far off compared to the fine scale model. If you use the upgrade design, we see a significant improvement in the performance compared to what we see in a proportional layering. And you can see where the transmod 80 layer and this fine scale, whether this arrow is wrong, the red dots is basically what fine scale layer model is. And you can see that after combining the upgrade and transmod, we can match the results reasonably well. Our results are slightly less optimistic than a fine scale model, but in general, the results really are excellent. So by combining the proportional method, combining the upgrade and the transmod, we can really match the results. Now, I'm going to show you how easy it is to use this particular method. So what I'm showing you here is a vol model. This was actually published by Statoil. This field was abandoned in 2016, so they decided to give up all the information about that particular reservoir. It's in public domain. So I just downloaded that data, and it's highly faulted reservoir. So what we do is we use the upgrade method, which is right here. And what we drop is basically the permeability in a fine scale data. So I think there is a whole lot of permeability values here based on different methods which actually they have created. I'm just going to use arbitrarily these porosity values. So this is a porosity value which is dropped here. This is a fine scale model. Then I drop the permeability, which is right here. If you have net to gross ratio, it will be included in your calculation. If you have water saturation, it will be included. So for example, if you have a reservoir which is some of that reservoir is in the water lake and you don't want to give too much weight to those, then you can also add the saturation as well as net to gross ratio, because the weighting of how we combine the layers is dependent on how much hydrocarbon pore volume is in that particular reservoir. I click on this calculate and I just simply say apply. So when I click on the apply, what it does, it takes the 85 layer model and then is going to calculate basically to everything which is related to that particular reservoir. And you can see right here, this is our design plot, and you can pick certain number of layers based on this. Or if you don't like this particular graph, you can use the heterogeneity index plot, which shows you basically how the different values of heterogeneity result in based on the number of layers you have. So if you decide that I want 50% or 60% of heterogeneity preserved, then I can just click here and it says you have selected 25 layers, and if you want, then you can just say okay. So I created 25 layers and it will create that 25 layer model, and you can do the quality check after it has done this 25 layer modeling. And if you click on this okay, it shows you basically coarse text which you can use in Eclipse directly, or this is a layer design. It shows you what one layer, first layer is combination of layers 1 and 2 from the fine scale. So it shows you all the details, including the fractions which are included in each of the individual coarser layers. And you can do the quality check. You can see this is the average permeability values. You can do Lorentz plot if you want to compare different wells. So if I click on the well, say 1519A, and execute, it shows you the Lorentz plot at that particular well based on the coarse scale which we have created versus the fine scale data. So any well you can check it. So for presentation purposes, if you want to justify certain number of layers you have selected, you can show all these graphs to make sure that people understand why we have come up with these layers. Once you have done this, you can just click on this create coarse grid. And what it would do, it will immediately take the fine scale data and appropriately combine the number of layers which you have determined based on this upgrade method, and it will generate a model which only has 25 layers, which is what we have selected. So it will create that coarse grid, and that's what it's doing right now. And you can see that the process is fairly quick in terms of how this coarser model is selected. So once it finishes the coarser model creation, which it has done, I'm just going to cancel it. And if you go at the bottom around the models, you will immediately see that there is this 25 layer coarser grid, which has been created right here. And now I'm going to use the transmod to create the transmissibility modifiers for that particular method. So I take the transmod and I'm going to take the fine scale properties, which are permeability in X direction, permeability in Y direction, permeability in Z direction. I'm going to take the porosity from that model. And then if you have net to gross ratio again and saturation, you can input this. Our coarse scale model is this 25 layer model. So I drop that. Then I need to browse the file for layer design, which I have already created when I use the upgrade method. And I drop that and I say, okay. So what it is going to do now is going to take the fine scale properties we already have available in the fine scale model, and then going to create the upscale properties for the 25 layer model. And the properties which are created in the coarse scale method include the permeability, core scale permeability in X direction, core scale permeability in Y direction, core scale permeability in Z direction. And not only that, it is also going to create the transmissibility modifiers in X direction, transmissibility modifiers in Y direction, and the transmissibility in Z direction. People who have done simulation understand that adjustment of the permeability in the upscale process can only go so far. If you really want to preserve the connectivity, which is observed in the fine scale, versus the connectivity which is observed in the coarse scale, the only solution you have is really to making sure that the transmissibility across the grid blocks is preserved. And what this particular transmod does, it provides you with those modifiers, and you can directly use them, those modifiers basically, as a way to capture either the presence of connectivity or the lack of connectivity. Because what happens many times is that when you build a fine scale model, and especially if you have like a sand shell type of distribution, that sand may be connected to shell, shell may be connected to sand, and there is really no flow. And you can see that in fine scale, especially for laminated sands. But once you coarsen the model, the average properties simply do not go from 0 to 1 or 1 to 0. And so you create an artificial connectivity. And this is true also in vertical direction as well as in horizontal direction. Sometimes the connectivity in the coarser model will be pessimistic. Sometimes the connectivity in the coarser model is optimistic. In vertical direction, for example, even one grid block is shale, then the permeability becomes 0 and you have no connectivity. When in reality, it's possible that the convoluted paths will create that connectivity. So you want to preserve that type of connectivity. And what you will see here, if I click on the properties and expand it, you will see that there is a coarse permeability in X direction, coarse permeability in Y direction. You have coarse porosity, which is just an arithmetic average, coarse permeability in Z direction. But more important, you have the transmissibility in Z direction and transmissibility multiplied in X and transmissibility multiplied in Y direction. And those are the values you input in Eclipse simulator, and that's it, you are done. So you can see how quickly we can take the fine scale model, decide on the number of layers you want to choose using the upgrade method, and make sure that you use the transmissibility multiplier so that whatever connectivity you have in a fine scale is also preserved in a coarse scale model. So this is basically the part which is related to conventional reservoirs. Let me go back to unconventional reservoirs because that's also important, because unconventional reservoirs typically have very complex grids and the wells can produce under transient conditions for a long time. And there are a lot of geological uncertainties. You could have physical properties such as permeability, porosity, compaction, adsorption. You have completion uncertainties like how should I define the fracture height, fracture length, number of successful fractures, because you sometimes have a lot of perforation clusters. We don't know every perforation cluster there is a fracture. SRV volume, the permeabilities of the fracture and SRV. So if you want to really capture the uncertainty when you build a model for unconventional reservoirs, you want to capture that. That means you have to do history matching of these wells very quickly. So we have two plugins which actually can help you in this particular methodology. One is called AutoGrid, which allows you to create automatic gridding once you define how many fractures you have, how many perforation clusters you have, how successful you are in terms of what is the average fracture length. You input that data and it will automatically create a grid which defines it. And then we have another plugin which is based on some of the patented technology which was developed at Texas A&M. It's called Link Unconventional, which uses a fast marching method, and it generates basically an equivalent 1D grid from the 3D simulation grid. And that makes our upscaling so efficient, because even though you may have multi-million cell model, which is capturing all the details of the fracture, we can create an equivalent 1D grid, which is only maybe 100, 200 grid blocks, and our simulation becomes incredibly fast. So this is an example of AutoGrid, and you can see how the grids are created. These are grades which are based on basically where the fractures are. And for this 1D simulation, the methodology we use is that we take the 3D model, we calculate the time of flight. This is called diffusive time of flight using fast marching method. And then we calculate the corresponding pore volume as a function of diffusive time of flight and how the volume changes. So essentially, we can calculate the speed at which the pressure wave travels in the reservoir. And using that, we determine the pore volume and how it changes as a function of this diffusive time of flight. And this is again function of diffusivity. And then discretize this volume. And we can transform this data and into an equivalent 1D grid, and the rate at which this diffusive time of flight and the volume is changing will tell us about the transmissibility across those grid blocks. So we calculate that derivative transmissibility, and then we can transform the data in equivalent 1D grid and run the simulation. So tau coordinate becomes our new coordinate. So instead of modeling everything in 3D grid, we assume that this tau coordinate is kind of an equivalent equipotential line, and we can utilize that and transform the data into an equivalent 1D transformation. And you can see how fast it runs. If this is a link unconventional simulation, it took only 7 seconds. It's basically single phase gas, and so it's very fast. If you look at the black oil model, this is Woodford case. And again, we are comparing basically the results coming from link unconventional with from Eclipse, and you can see the results match reasonably well, but our simulation time is about 230 times faster than conventional 3D simulation. And more complex the physical process, more advantage you gain in using our methodology. So here you have a compositional simulation, and our simulation time is 3,400 times faster than conventional simulation. Now, the main application of our methodology is history matching, because you can generate all kinds of reservoir descriptions, and you can do the history matching very quickly using your 1D method, and rather than waiting for hours and hours and hours to finish the 3D model. So here's an example from a Midland well. It's a black oil model, undersaturated. The length is about 7,500 feet with 40 stages, and there are 4 perforation clusters per stage. And what I have done is I have created multiple realizations with different fracture height, different fracture length, different SRV volumes, different cluster success, different probability of SRV, different fracture probability. So you can try all kinds of things in terms of completion variability, but if you want to look at the variability of the reservoir properties, you could do that. Then we constructed the 3D model using AutoGrid, and we use the link unconventional for history matching, and typical runtime for history matching is less than 1 minute. So you can run the model very fast, and we basically changed the parameters to match the water cut, which is the water saturation in fractures, gas and oil related permeabilities within SRV region, permeabilities of fractures in SRV regions. And once we match the history, the same data inputs were used for 3D run. So we took the parameters from 1D, just simply put it in 3D, and we just wanted to see how close we are with respect to 1D and 3D. So you can see the different realizations. On the left-hand side, I have fractures. On the right-hand side, if you have 100% SRV, everything is SRV. But we also looked at different realization. You can see in this case, the fractures have different heights, the fractures have different lengths, different percentage of SRV volume. And so you can create all kinds of realizations, different heterogeneities, different SRV volumes, different fracture length, and you can history match using this 1D simulation very quickly. So these are the results of history matches of 6 different models. And you can see the bottom hole pressure is matched reasonably well. Oil rate is, of course, a constraint. Gas rate matches okay. Water rate matches till October 2017, but after that there's another well which of course is fractured, and you see an interference. Of course we cannot match that part. And here is the result from the 3D model. And so we took the parameters from 1D model and put it in 3D model, and the results don't match as well as 1D, but it's not that bad. So you can see that the results actually from 1D and 3D compare well, but the difference is that 1D model takes about a minute to run. The 3D model takes about 3 hours to run. So obviously, if you tried to do history matching using the full-fledged 3D simulator, that would have been very difficult. So 3D models were not history matched, just 1D parameters were used to run 3D models. Therefore, the history matching is slightly worse, but the simulation time is big difference. So you can achieve the history matching using 1D model in a couple of hours. Basically, you can change the parameters, you see how good the results are, change it again. But the main reason we want to do 1D history matching is that when you look at the future performance, because ultimately purpose of the history matching is to predict what's going to happen in the future. So here is the prediction for realization 1D versus 3D. There's some difference, but not that much. Here is again, for another realization, what is the difference between 1D and 3D? And there's some difference, but not that much. But more important, and this is the point I want to drive at, is that if you use 1D model, create multiple realizations, and do the history matching very quickly, and compute the uncertainty in the future performance, you can see the bounds of uncertainty, which are captured by 1D, are very similar to the bounds of uncertainty we'll capture using 3D model. Because if the goal is to predict the uncertainty, you can significantly save time in doing the simulation by using the 1D model. And at the same time, by creating multiple models, you can capture correctly the uncertainty. Imagine if you are using the 3D model and doing the history matching, it would have taken so long to do history matching of one model that more likely than not, you would not have been able to properly capture the uncertainty. So here's the benefit of using the 1D model. So for both conventional and unconventional formations, geocellular models can be significantly upscaled without compromising the dynamic behavior of a fine-scale geocellular model. For conventional reservoirs, basically we have Petrel plugins, Connect Upgrade, and Connect Transmod, which can help you to optimize the number of layers in simulation model and preserve the transmissibility observed in the fine-scale model. For unconventional reservoirs, we have two different plugins, Link Unconventional and Link Auto Grid, and that allows you to create the grids very quickly and do the simulation very fast, thus reducing the simulation time. I have one more slide, but I want to go back and show you how easy again is to run this unconventional simulation, and I will go back and finish my presentation. So if you go to Petrel, and you can see at the bottom, you have these results. And so you can see that these are basically my 1D models. And I've created those 1D models and run the multiple simulations and history match most of those models. And how easy it is as simple as this. You drop the 3D model, because just like when you're running a 3D simulation, you're going to construct a 3D simulation model. So you create that 3D simulation model and you drop that simulation case right here. And then you run this 3D no sim. What 3D no sim does, so you first click on that run 3D no sim, and what that run 3D no sim does is basically runs under no simulation, initializes the 3D model, and captures all the properties, physical properties, especially the oil and gas physical property like compressibility, using that no sim method. And once you do that, then we use that information, generate the tau contours, and run the simulation. So if I click on this run simulation, what it is doing is now is going to run basically your 1D simulation. And what that requires is taking the data from 3D model, so all the physical properties such as permeability, porosity, saturation, as well as the physical properties which you have calculated. Then it will take that information, calculate the compressibility of each individual grid block, because you need the compressibility of individual grid blocks so that you can calculate the speed at which the pressure wave travels. Remember, this fast marching method is based on the traveling pressure wave. So we can calculate basically the speed at which the pressure wave travels. And once you calculate the speed at which the pressure wave travels, it will generate basically the values of tau, or this diffusive time of flight, for every individual grid block, and using those tau contours and how fast those tau contours are moving. Remember that inside the fracture, where the permeability is super high, the values of the tau contour is going to change very quickly. Whereas if you have matrix where the permeability is quite low, then the tau contour is going to move fairly slowly. So you generate these tau contours, tau values, and then for equal values of tau, we create the tau contours. And essentially, you can think about these tau contours. The constant value of tau is basically that particular value of tau, the pressure has reached exactly at the same time. And so it becomes an equipotential line. And we use those equipotential lines, and then within each tau contour, we average all the physical properties, and that way we can reduce basically our 3D simulation into an equivalent 1D simulation. What we have to remember is that when you generate a 3D model, it's highly heterogeneous. Obviously, you could have variation in the physical properties, you could have variation in the compaction of the permeability. So there are a lot of things which could vary within that 3D model. And what we are doing is that within each tau contour, we're taking all those physical properties and we are averaging those physical properties so that we can construct equivalent 1D model. But because there is a significant upscaling of the physical properties, the match between 1D and 3D model is not going to be perfect. You're going to see some variation in the 1D model and 3D model. So I don't want to claim, when I'm showing you these results of 3D versus 1D simulation, that when you run a 1D simulation, you are going to get exact match. I mean, in this particular case, I'm showing you, you are getting a reasonably good match between the 1D and 3D simulation. But it is not always the case that 1D and 3D simulations are going to match exactly. But what is advantageous in using this 1D simulation is that if you are able to generate multiple realizations considering wide possible variations of 3D model, then you are going to be able to capture the uncertainty very quickly. So right now what it is doing is that it's running that 1D simulation. And if you look on the screen, you can see how fast that 1D simulation runs. I mean, literally, it will take just less than a minute before the simulation is finished. And then we have the results. And then we can compare those results with the historical data. And if you don't like the results and if you don't like the comparison, you see it's finished. It's already finished. So you can see how quickly, I mean, most of the time, unfortunately, in this particular process is not really the simulation itself, but how long it takes to process the data and utilize that information. But you can see the simulation time is very quick. And I can guarantee you that if I would have run this same model in 3D scheme, it would have taken 2.5 to 3 hours for me. So 1 minute versus 3D simulation. And if you look at the results, this is your 1D result, and then if I go to the chart 3, these are the 3D results. So there is some difference in the 3D versus 1D result, but the amount of computational effort which is required to run this model is so much more than if I would have run the 1D model. So again, useful upscaling process where you can significantly reduce the time and still achieve the results which you desire. So I've already stated the summary. I think that let me talk about what is our interest in making this presentation. The interest is that we have been developing the Petrel plugins really since 2007. I think we have been user of Petrel since 1998 when Petrel was first introduced. So we have developed a large number of Petrel plugins which are commercial, And we can also build the workflows which can make your Petrel task easier. So we can build customized Petrel plugins for you, which can make your routine job easier. But our interest is not necessarily just building the plugins which can make your routine job easier. I hope that by listening to this presentation, you realize that we are interested in capturing the latest technology. So it's not about just simply doing your physical job better, but adding some value to it, and the way you applied some new technologies so that can make your job easier in terms of finishing something faster, but also you'll use the latest technology which is currently available, which can be utilized to make that Petrel plugin better. So we can easily customize a workflow or a Petrel plugin for your purposes. In addition to that, if you are stuck with some questions about Petrel, maybe an hour of work which will require to ask us some questions related, hey, how do I proceed with, is this the right method to choose for this upscaling? Or when you're generating the properties of the reservoir, what are the assumptions we should make, why should not make? A lot of times when you're using Petrel, a lot of the questions come to your mind, and a lot of times you make subjective decisions, and your result, ultimately the reservoir description you construct, is really based on those subjective decisions. So if those decisions are wrong, the resulting reservoir you construct could have a lot of flaws. And what we can help is making sure that you are making the right assumptions so that when you build the reservoir models, you can defend the assumptions you have made in terms of different algorithms you have used in reservoir properties. So these are like small things we can help you to make sure that your job is better. So this is my last slide, and I'll be happy to take questions if you have any.
Great. Thank you, Mohan. We're starting to get the questions already. I'd like to remind your audience that you're muted, so you can ask your questions using the GoToWebinar question feature, and you will be anonymous. So here's a question. Can you go over the Transmod plugin? How do you determine the transmissibility multipliers and yet preserve the heterogeneity?
Yeah.
Is it some kind of a weighted average?
No, I want to explain to you. So the way we calculate the transmissibility is that if you have a fine scale information, which you have, obviously, because you have a fine scale model, and we can calculate the transmissibility in horizontal direction, in X and Y direction, by knowing what the fine scale transmissibility is. Then when we go to coarse scale and use the coarse scale properties, we can also calculate the transmissibility in a coarse scale. And using that information, we can easily calculate what the multiplier should be so we can preserve the fine scale transmissibility. In vertical direction, the problem is a little bit more subtle and more complicated. So if I could just, I don't know whether I can, but let me just try that. If I could draw a picture in vertical direction, let's assume that here is your grid block at the top, here is the grid block at the bottom. These are the upscale values, and this is your interface. And let's assume that your fine scale grid blocks are like this, and fine scale grid blocks are like this. So what we do in this case, and again, this is really the method which is developed by Mike King from Texas A&M. We are just utilizing that information. So if you have a shale here and shale here, then when you calculate the vertical permeability in the upscale grid block, it is 0. And when we calculate the vertical permeability in this grid block, it also is 0. So the transmissibility will become 0. But in reality, you could have flow which may go like this. So there is always a possibility that still there is a flow observed. So the way we calculate the transmissibility in Z direction is we use the fast marching method again. And from the interface, we go in both directions, from this direction and this direction. And we can calculate what is the connected volume which can see each other. So in this case, the top 3 grid blocks and the bottom 1 grid block are connected to each other. So depending on how much volume out of the total volume is connected. We calculate the transmissibility in Z direction. You provide that information. So transmissibility Z direction is really based on the methodology, which is not yet published, but it is based on the fast marching method. The transmissibility in X and Y directions are basically calculate the fine scale transmissibility, calculate the coarse scale transmissibility, and just calculate the ratio of the two and provide you with the transmissibility multiplier. Sorry for a long answer for a short question.
Next question. The grid size remains the same in the upscaled layer?
The grid size in X and Y direction remain the same in upscale layer. And I can give you a long philosophical reason for this. But the short answer is that we do not prefer that you upscale in X and Y direction. And the reason is because the grid blocks in X and Y direction are arbitrarily selected. There is no sound basis why we select certain grid blocks. So start your model with the coarsest grid block possible, which you can utilize in your simulation model. What we need to upscale is really in vertical direction, because we have tremendous amount of data in vertical direction based on geology, core data, and log data, and you want to preserve that heterogeneity in vertical direction. So your vertical gridding is much more refined than horizontal gridding. So preserve the horizontal grid block the same, just upscale the vertical grid blocks.
Okay, the next question. If we have a complex DFN for naturally fractured reservoirs, will the autogrid be able to capture the effects of the vertical heterogeneity? As we saw, it's a 1D simulator.
Yes. So the answer to that question about the 1D simulator, which is the unconventional simulation, is that we have the dual porosity option. So the way we actually use the 1D simulation, when you have a dual porosity model, which is the fractures explicitly defined, and you have a fracture permeability as well as the matrix permeability, is that we use the fracture permeability to calculate the speed at which the pressure wave travels, because we assume that that's the higher permeability and that's what determines how the fluid is going to move. But you have the option of dual porosity model, so you can utilize that dual porosity model and run the 1D model just like your 3D model will run.
So the next question is kind of philosophical. If the 1D and 3D simulations result are almost similar, why do people always want the 3D simulation?
I think that the answer to that question is that it is not true that 1D and 3D simulation results are always going to match as well as I have shown you. I think there are situations where the 3D and 1D simulation results may not match exactly, but what it provides you with the 1D simulation is that if you really are so married to 3D simulation because the heterogeneity in a fine scale is really well captured, your initial parameter selection based on the 1D match is always going to be a good starting point to finish your history matching using 3D model. But what I was trying to show you is that even though the results of 1D and 3D match are not perfect, they're not going to be that far off, but let's assume they are not perfect, not within the limits of error you want to imagine. You still be able to use the 1D model, finish the history matching using multiple different realizations, multiple different possibilities, and then you'll be able to capture and quantify the future uncertainties. And that's the beauty of using a 1D simulation, that if you had done same effort and match multiple models using 3D models, and you would have captured the uncertainty in the future performance. The bounds of uncertainty are not going to be different whether you use a 1D model and 3D model. And then the amount of time it takes to do 1D model is so much smaller.
Next question. How do we make sure the connectivity is consistent from the fine scale to the upscaled one?
So what we are really realizing, and in any simulation process this is true, is that the simulation does not care about the permeability of the grid block when it's running. Simulation cares about the transmissibility across the grid blocks when it's running. So what we try to do in this transmod is preserve the transmissibility rather than permeability, because you can adjust the permeability as much as you want, but if you don't adjust the transmissibility, you will not be able to match the results. And I just explained just a few minutes ago how we make sure that the transmissibility in X, Y, as well as Z direction is preserved using our methodology.
Is there any relationship between net to gross and the layering?
So yes, I mean, the way I think our algorithm works is that if you have high net to gross ratio, that means you have more sand than shale, then those grid blocks will receive a bigger weight because you want to preserve those grid blocks which are contributing the most to the performance of the reservoir. So we preserve that. If you have a shale, I mean, so for example, very low net to gross ratio in a part of the reservoir, which you have a 80%, 90% shale and very little sand, then obviously those are the grid blocks which could be combined much easier because there is not as much volume of oil within that part of the reservoir. So yes, net to gross ratio does matter in calculating the how we decide on the weight of individual grid blocks when we are combining the layers. The second effect the net to gross ratio has is really computing these transmissibilities, as I mentioned to you before. Because in a fine scale model, if you have laminated sand and you have really thin layers of sand and shale and shale and sand and shale and sand, and then they just kind of alternate between them, then when you upscale the model, if you use a traditional method of calculating the vertical permeability, it will always go to zero because there will be at least one fine scale grid block which is shale, and so you will simply cut off the communication in the vertical direction. And we try to preserve that connectivity, even though you have this classical laminated sand shale distribution in the reservoir.
Thank you. I think that's all the time we have for questions. I want to remind everybody that later today you will receive a link to a recording of today's webinar, an evaluation form, and more information about the consulting services that Dr. Kelkar will be providing. So we really appreciate all the great questions today, and thank you for your participation. Goodbye.